Hello, this is part 2 on our section about piecewise functions. And the example we're going to do in this video is to find the volume of a 2-liter bottle, and we're going to do that by first finding the outline of the shape here. So take a moment, pause the video, and see how you would do it on your own, and then we'll talk about it together. So the first step of the modeling process is to define the problem and make some simplifying assumptions. And notice there's already an assumption here about assuming the bottom of the bottle is flat. And that really comes from a bigger assumption is we want to assume this is a solid of revolution so we can use calculus to rotate and calculate a volume. So that means we really just need to find this function here along the edge of the bottle. And we're just going to use the straight part here and the curved part here. So we're also going to ignore the threaded part there at the top. Now, that means we're going to lose some volume. That's okay. And on the other hand, for some applications, for instance, what if I wanted to make this a water clock and I'm going to drill a hole right here at this point on the bottle and I'm only going to fill it this high, then that's only part of the bottle I'm going to care about anyway. So now we need to take some measurements. And notice it's about 15 centimeters before we start to get the curve of the bottle. And it looks like about 21.5 to the top of the bottle. We can also measure the diameter of the various points. And from that, we should get an outline that looks something like this. As you can see, it's not a perfect fit, but it's good enough for our purposes. So the next step is to calculate this function. So notice it's a piecewise function where our domain ranges from 0 to 15, and then 15 to 21.5. The first function, of course, is not bad. That's 5.4, just a horizontal line. But it's this curved part that's a little more interesting. So let's assume that's a parabola. And if it's a parabola with a vertex right here, well, then we have enough information to calculate that as a function of, let's do x as a function of y. So our function is going to be of the form a, which we don't know. We just know that it's opening to the left, times the quantity y minus the y value of the vertex, 1.6, that quantity squared, plus the shift to the right, which is 21.5. Now, we have a second point on the parabola, so we can plug that in to solve for a. X is equal to 15 equals a, y is equal to 5.4. And then we can solve for a. So a then is just going to be 15 minus 21.5 divided by this quantity 5.4 minus 1.6 squared. And if you work that out, you get around negative 0.45. And then we can solve for y to actually get our function of x. So in other words, if x equals negative 0.45 times y minus 1.6 squared plus 21.5, then I can move the 21.5 over and divide by the negative 0.45 to get y minus 1.6 squared. And then we can square root both sides. And so I get y equals 1.6 plus the square root of x minus 21.5 over negative 0.45. Or if we wanted to clean this up a little bit more, we could write 1.6 plus the square root of, let me move that 21.5 minus x. And then that gets rid of the negative sign, so 0.45. So this function will describe this outline. And now I can use calculus to actually find the volume. Notice this is a disk method problem, so the volume then should be the integral from 0 to 21.5 times the area of a circle, so pi times the radius squared, where our radius is f of x, dx. Now, we could work all this out by hand. Since we have access to a computer algebra system, we'll do that now. All right, so here is our maple file, and I've typed in the function that we just talked about, and here's a plot of it. Again, it looks like what we expect. Curve that's opening to the left, that's parabolic. And we can define a piecewise function in maple just like we wrote on paper, and there it is. And then this is how we can plot it. And it's always good to plot these things to make sure that the function that we've typed into maple matches what we thought we had typed in and what we're expecting. And this does, in fact, look approximately like the 2-liter bottle profile. Now, if we want an even better feel for what we're trying to do here, we can use parametric plot to get a 3D visualization. So notice I just use sine and cosine to rotate that piecewise function around the axis, and then use the t to run from one end to the other. And so this is our 3-dimensional visualization, and that looks pretty good compared to our bottle. And so now we can calculate the integral, which is right here. So I integrate pi g of x squared from 0 to 21.5, and we get 1739, which that's of course in cubic centimeters. So if I convert that to liters, I get about 1.7 liters, which, considering we ignore the bottom part of the bottle, that doesn't seem too far off. Now, could we get more precise with more data points and a more sophisticated piecewise function? Perhaps. Or maybe my measurements could be better, but for the purposes that we're trying to illustrate, we'll be satisfied with this model. And that's it for this example. We'll look at some more techniques in the next video. We'll see you there.